So this time we will learn about how exactly memory works inside the GPU or the device. So previously we have already seen how to write a simple CUDA kernel and run it on the GPU. Now let's warm up with the vector addition example. So before I can start anything, I have to import the numpy and the CUDA module from numba. I'll also get the float data type, which we will be using in the later part of this video, and I'll also get the math module. Now vector additions on CPU are done with a for loop, where we loop over every index of the both vectors and add them. But in the GPU, we can parallelize it and compute one sum at each thread. So let's write the program from the point of view of the device or the GPU. So first I'll use the CUDA.jet decorator, and after that I'll define the function. So I'll just call it f. Now we will be using one-dimensional arrays, and over here for CUDA.grid I have passed one dimension, and that's how we'll get position inside every thread. Now I'll set the size of the output buffer, and after checking if position is less than size, I can index the output buffer and add corresponding values from the both inputs, and that's actually it. So let's try to run it, and before that we have to create the grid itself. So n I am taking as the length of the vectors. So over here I have created a random array and send it to the device. And similarly I'll create another random array and send it to the device also. And see over here, I'm creating a device array like A. So what this function does is it will create an array on the GPU directly with the shape of A. So it will be a null array but with the shape of A. So once we have this, we can use f.forAll. So what for all does, it creates one-dimensional grid for the given size. So size I'm giving over here, length of A, it does not matter because size of A, B and C all are same. And after that I'm passing our argument. So for all will actually calculate and define the grid for us. After that we'll copy the output from the device to the host. So why this step is necessary? Because CUDA kernels cannot return anything. That's why we have to pass the C, which is output buffer, as a parameter to the function, and we are changing the value of C in position. So if I run everything, we can see the sum has been returned to the host. Now instead of using for all, we can actually manually define our grid like we did in the previous video. So over here I have manually defined the grid. So for the grid I have defined the blocks and threads. Once this calculation is done, I'll get the output from the device, and let's see. Yeah, the result is exactly same even with our custom grid. So moving on to matrix multiplication. I actually gave this as a task in the last video. So let's solve this. First we'll go over how exactly matrix multiplication works. So we are working with square matrices, and A and B are our input matrices and C is the output buffer. So to multiply two matrices, we have to get the row from the first matrix and the column from the second matrix and perform dot product on them. And the resulting value will go to the intersecting index of the output matrix. So previously I have also mentioned that the GPU or the device has its own memory. So whenever we create some array or transfer it to the device, we are actually using this memory pool, and all the threads which are in our grid have access to this memory. So to perform a matrix multiplication in a CPU, we have to loop over for every entry in the output buffer. So over here, there is a 4x4 matrix. We have 16 outputs over here. When doing matrix multiplication on the host, we have to run a for loop for 16 times to calculate each value. But in the device, we can create a grid which resembles the matrix itself, and each thread can take care of the output of each cell. Like that, the output will be computed for all of C at once. So let's implement this in Python. I will start with CUDA.jet decorator. After that, I will define the name of the function and all the input parameters. So the input matrices are two-dimensional. That's why I am getting the thread ID as a I, j pair. Now I'll put a condition so that no unnecessary computations happen, and after that I'll write a simple logic for multiplication and accumulation. So which is dot product over here. To perform the accumulation, I am defining a temporary variable and I am assigning it to 0. After that, let's write the loop. So this is how you will do multiplication and accumulation for the dot product. And once this dot product has been calculated for the I, jth thread in the grid, we can simply push that result to the output buffer I, j. And that's it for the matrix multiplication. So let's run this now. I'll create xh which has 16 elements and I'll reshape it to 4, 4. So we have a 4 cross 4 square matrix. Now Vy will be a 4 cross 4 matrix with ones. Now Z underscore H will be the output buffer filled with zeros. Now we have created all of these things on the host. Let's move them to the device. So X underscore D will have the data from X underscore H but inside the device. Similarly, we can create X underscore D and Z underscore D. Now we have all the input and output buffers ready. So let's build the grid. Over here, this is how I am defining threads per block and blocks per grid. So this is similar to how we did for the 2D sum. Now, to call the matmul kernel, I have to pass in these blocks per grid and threads per block to create the grid. And after that, I have to pass our input buffers and the output buffer. And lastly, I'll get this data back to the host. So let's run this. Oh, I actually forgot to print. So let's print this also. So as you can see, the matrix multiplication has been done. So this matrix multiplication is not optimal at all. So what do I mean by that? Let's go back to the slides and see what is actually happening over here. So when calculating inside one thread, we are getting the row and the column. And we are doing this inside a for loop, right? Inside the for loop, we are looping over all the data of the first row and all the data of the first column from A and B respectively. So first we are accessing 1, 1 from both A and B. After that, we are accessing 1, 2 and 2, 1 from A and B. Next, we are moving on to the next data, and like that, we are looping over the first row of A and first column of B. But if you have noticed, every time in the for loop, we are talking to the GPU memory pool and we are trying to pull a data from the GPU memory pool. So in the previous videos, we have already seen that data transfer is a costly operation. Between host to device, this takes a lot of time, but this memory is already on the device. So from device to the thread itself, also this takes time. That's why our current matrix multiplication is not optimal at all, because every time we are in the loop, we are accessing data directly from the memory pool. And even though this memory pool is on the device itself, talking to this memory is slower. So what can we do to improve this? Let's see. So there is a portion of memory in the grid itself which is very fast, and this is locally available to the threads. This memory is called shared memory, and this is shared between all the threads in a block. So this shared memory will look something like this. And now we can actually preload the data from A and B and use this shared memory during the for loop, which will be much more faster than directly talking to the GPU memory pool. So let's try to implement this shared memory thing. For that, I'll first define thread per block. Let's write our CUDA kernel. So after the CUDA.zip decorator, I'll give the name first matmul. And I have given it both of the input buffers and the output buffer. So let's define the array in the shared memory. So over here, we have defined the shared memory to have this threads per block, threads per block shape. And the data type we are providing it as float 32. Now if you have noticed, we're actually declaring this shared memory inside this kernel, and from the previous video if you recall, a copy of this kernel will be passed on to each thread and they will run separately. So in theory a multiple of this should get created for each thread, right? But that's why the shared memory is different. So inside all of the threads, whenever this shared memory is declared, it will also share the location and the indices. So even though this will be run multiple times in every thread, multiple reference of this will be created but not instances. So there will only be one shared memory and we are referencing that shared memory inside every thread. So this is my SA and SB. Now to get the absolute position of the thread in the grid, we can do this CUDA.grid, then I will pass the dimension we want. So 2 over here. And I'll also get the thread IDs and blocks per grid. Now previously also we did each thread computes one element in the result matrix. So temp over here I am defining as float 32 of 0. And now inside this for loop I'll preload the data. So this for loop will iterate over the required data to calculate one value of the output matrix and preload that much data only. So once we have this preload operation done, we can move on to the next step. So before starting the multiplication and accumulation for the dot product, we have to actually wait for all the threads to sync. Why this is needed, I'll explain in a moment. So this is where our multiplication and accumulation is happening. But unlike previously, we are accessing the shared memory instead of the device global memory. So this operation will be much more faster this time. So after that we can do CUDA.sync threads again, and I'll come back to that in a moment. And finally we can assign our dot product to the respective output buffer index. And that's it, our modified version of the matrix multiplication using shared memory. It's time to run this. So over here I have created the same data buffers as before. And over here I have also calculated threads per block and blocks per grid to create our grid. And we have everything to call this function now. So let's do that. So I'm calling this matmul. And in the end I'll get the result from the device to the host. And I'll check for if the output is equal to a normal matrix multiplication done on the CPU or the host. So this @ symbol is a built-in Python function to multiply two matrices. So let's run everything. And as you can see, true has been printed. So our multiplication logic is correct. Now coming back to why this CUDA.sync thread is required, let's remove this and let's run our program. So as you can see, false has been printed. So what happened? Suddenly our matrix multiplication is logic cannot be wrong, right? We just saw that it was correct. So if I go back to the slide, what happens is the execution time of all of these threads are not same. Let's say thread 1 has preloaded the data and modified the shared memory. But as I said, this memory is shared between the different threads and our thread 2 is very slow and it has yet to preload the data. So the data in the shared memory has already changed by the time the thread 2 is trying to modify the shared memory. So like that, one thread's performance can affect other things also. So this shared memory needs to be preloaded for all of the threads and then we can proceed to perform our matrix multiplication. That's why syncing after the preload and syncing after the operation of the matrix itself is required. Otherwise the result of the matrix multiplication will be wrong. So that's it for today. And next time we will see some other very useful functionalities that are also inside the numba library. Thank you for watching this video. Thumbs if you liked it. Do share it with your friends and family. And make sure to subscribe for more content and let me know in the comment section below.